Okay, I'm back. Sorry about the interruption earlier. This was a very important administrative thing which I had to do. Now, where was I? So we were talking about the lecture series that I'm going to give on closure curves at the Korean Institute of Advanced Study. And like I said, we're going to talk about curve shortening flow, curve diffusion flow. We're going to cast these guys in an abstract gradient flow framework. And then we're going to speak about more complicated flows, the generalized Hilbert flow, as well as the affine curve lengthening flow, so long as time permits. And now I just wanted to give you a little overview of the key papers that we'll be looking through in the course of the lecture series, and some sort of signposting for the course so that people know what to expect. Okay, so then I'm going to pick you up again. Now the focus on my digital camera is quite poor, so you'll have to excuse me. But you'll have to trust me that these papers are what I say they are. So the key papers on the curve shortening flow are the following. So this is the heat equation shrinking convex plane curves by Gage and Hamilton in the Journal of Differential Geometry. A distance comparison principle for evolving curves by Gerhard Husken. This is in the Asian Journal of Math. The heat equation shrinks embedded plane curves to round points by Matthew Grayson. This is in the Journal of Differential Geometry again. And the more modern paper is the curvature bound for curve shortening flow by distance comparison and a direct proof of Grayson's theorem. This is in Krell's journal, just 2011, very recent. So I won't be going through every single thing in these papers, but I will be trying to go through most of the things. Although in Grayson's paper I will spend most of the time just talking about the idea of the proof, and the actual proof of Grayson's theorem I will use this paper for. Now when I'm going to cast things into an abstract gradient flow framework, there isn't really a paper that I can use, so I'll develop this material from scratch. But in terms of the results on the particular flows, I will be going through this paper of Chuk-Kubert and Schätzler, the evolution of elastic curves in Rn, existence and computation. This is in the Siam Journal of Mathematical Analysis. This has results for the elastic flow, constrained elastic flow, some very, very simple version of the generalized Helfrich flow, and curve diffusion flow. Importantly, a blow-up criterion for curve diffusion flow, which I will go through in detail. Now, more on curve diffusion flow can be found in this paper of Elliott and Garke. This is called Existence Results for Diffusive Surface Motion Laws. Don't worry about the word surface here. The main result that I'm going to use is for curves. And this main result is using a completely different method to this paper. This is my paper on the curve diffusion flow of plane curves. It's in Nali di Matematica in 2012, where I present a more geometric proof of this result from Elliott and Garke, some other results on the curve diffusion flow, and some improvements in terms of regularity and things like this. We'll talk about this in detail in the lecture series. Another paper of mine which I'd like to go through, which works more in this gradient flow framework, is the global analysis of the generalized Helfrich flow of closed curves in Western Rn. This is on the archive. It's not published yet. It's very new. And this deals with a rather complicated functional which may or may not have invariances, and establishes some analogues of the results of Chuk-Kubert and Schätzler, as well as actually improving their results in the end. Okay, now if I have time left, I would like to talk also about the affine curve lengthening flow. This is from the Krell journal in 1999. This is by Ben Andrews, and this is again in the gradient flow framework, but here we take the affine length functional and we actually maximize the affine length functional along the flow. And so this is a very, very interesting idea. This is a very fundamental idea actually from the perspective of invariant flows in geometry. But it's very difficult to analyze in terms of PDE, in terms of mathematical analysis. But of course Ben, he's managed to do it. He did it quite a while ago as well, and I think that this is really a fantastic paper which we should try to go through if we have time. Okay, so now, the basic plan is as follows. The theorems which we want to prove in the course, definitely, are the following. 1. For curve shortening flow, we are going to prove in detail that convex plane curves shrink to points. 2. For the curve shortening flow. We are going to improve the theorem, and we're going to prove that embedded plane curves shrink to points. Now, the literature for this is, as mentioned, Gage Hamilton, Huskin, Grayson, Andrews, Bryan. I estimate this is going to require 4 lectures. The third thing which I would like to prove in detail is this gradient flow framework that I've been talking about. So the curve flows, cast the curve flows as gradient flows of functionals in a given function space. Okay? So this will encapsulate every gradient flow that we're going to talk about. Every single flow of curves that we're going to talk about can be thought of as gradient flows of a function. Okay, now for curve diffusion flow, we're going to talk about the existence of the flow, we're going to local existence, we're going to talk about blow-up. Now this is something new, this is something that we didn't see before, this is where we don't have global existence. And then we're going to talk about when we do have global existence, we're going to talk about stability of circles. Okay. Now, other flows we're going to talk about, this is 4th order, of course, is the elastic flow. This is the gradient flow of the curvature in L2. And the generalized Helfrich flow, which is the gradient flow of this generalized Helfrich functional. And we're going to give global existence and asymptotic analysis for these flows. Okay. And then the final flow, if we have time, is the affine curve lengthening flow. And we're going to do global analysis, as well as asymptotic analysis for this flow. Now, the literature relevant here is Chuk, Kuvert, Chetzler, Elliott Garker, myself, and Ben Andrews. Okay, now all of these papers added together are 211 pages. That's quite a lot, and I'm not crazy. I don't think that we can go through all of this, but I will try to go through most of it in detail. I think that we can manage most of it in 8 lectures or so, and I will try to keep the exposition as fundamental, as rigorous, as detailed as possible throughout the entire lecture series. There is no real background required. Some undergraduate mathematics will be required, some essential calculus will be required, PDE, partial differential equations, parabolic partial differential equations are not required, but would be helpful. I will go through what's required in the course. Some geometry would be helpful, again, but it's not required. I'll go through what we need in the course. I'll talk about reparameterization, diffeomorphisms, things like this. Functional analysis, again, it's not required, but would be helpful. I will develop this from scratch when I talk about these gradient flow structures. And other than this, really, we just have to have fun. It's going to be really enjoyable, I think, and I encourage everyone who is able to come, meet me, talk to me about maths, about whatever you like, and